Okay, so in this video, we will consider our first application of the central limit theorem. So here's the setup. Suppose that in our population, so imagine that you have a population. We'll consider here individuals. It could be the city, Quebec City, it could be Montreal, it could be the entire province, but suppose you have a large population of people. And suppose we consider the proportion of people that own a cell phone. Suppose that in our case, we'll assume that 70% of people own a cell phone. Okay? So suppose we have this population, and we know that roughly 70% of people from this population own a cell phone. And here's the question: what if we sample 120 people? So suppose that we sample, so from our population, we take a subset of our population, so we sample at random 120 people. So from our population, we take a random sample of 120 people. And what if we ask, out of this sample, what is the total number of people that own a cell phone? So we'll let x, and again, this is a random variable, because if you think of it, if you take a random sample of 120 people, and I do the same thing independently of you, most likely we'll have, from both samples, different numbers of people that own a cell phone. So x is a random variable. That value will depend on your actual sample. So suppose we let x be the number of people. That own a cell phone, so the number of people who own a cell phone. From our sample. So from our sample of 120 people. Suppose we ask the following question. We're saying we randomly choose 120 people. We count from this sample how many people do own a cell phone. And what if we ask for the probability that x is at least, say, 90? So at least 90 people from our sample will own a cell phone. So here's say what we want, the question we want to answer. We want the probability that at least 90 people from our sample of 120 people do own a cell phone. Since our random variable x is the total number of people from our sample that do own a cell phone, we are asking for the probability that x is at least, so bigger than or equal to 90. So that's what we want to find. Well, every time you want to find a probability involving a certain random variable, all you need is to figure out the distribution of this random variable, and from the distribution you can compute the probability. So let's ask ourselves here, what type of random variable do we have? So what do we know about this random variable? Well, think of it, right? You can think of each person being a single binomial experiment, right? Imagine yourself, you've randomly selected 120 people, and now you will ask one person after the other whether or not they own a cell phone. So imagine yourself, you pick person 1, you ask, do you own a cell phone or not? If they say yes, you add 1. If they say no, you add 0. And you keep going. So every person is a binomial experiment. You will either have an answer of yes, which is a success, or an answer of no, which is a failure. And because we repeat the experiment 120 times, and we assume that since we are sampling people at random, we assume that the people are independent of one another. So what we have is a sequence of 120 independent Bernoulli experiments. Therefore, x is a binomial random variable. And the question is, what are the parameters? Well, if you remember, we have to specify the number of trials and the probability of success for each individual trial. Well, here, since we sample 120 people, we repeat the experiment 120 times. And each time we pick a person, the probability of success, which is the probability that someone does own a cell phone, is 70%. So the probability of success is 0.7. So, in theory, now we're good to go. We know that x is binomial, and we have 120 trials and the probability of success of 0.7, and therefore, of course, the probability of failure is 0.3. Well, let's see now if we attack this question directly. Let's see if with this distribution, that is the binomial distribution, if we can provide an efficient solution, or will it involve a lot of work? So now think of it this way. We are looking for the probability that x is equal to or is greater than 90. What does that mean? Well, it means that x is either exactly 90 or x is exactly 91 or x is exactly 92 all the way up to 120, right? Since we're sampling 120 people, we cannot have more than that number of people owning a cell phone in our sample. So all the way up to p of x being equal to 120. And this would not be hard, right? Because we know that if you have a binomial experiment, the probability that you observe a given number of successes is simply out of the number of trials, in our case 120. We choose our x successes. We are saying success x times, therefore we are saying failure, in our case 120 minus x times. So we do have the probability distribution for the binomial distribution. So we could find p of x equals 90 by plugging x equals 90 in here, then plus plug in x equals 91, 92 up to 120. But if you look at this, we don't really want to do that. That's way too much work. And you might think of the complement, but the complement is x is less than 90. So that would be x equals 0, 1, 2, 3 up to 90. That's even worse. It's even more work. So sure, we could find the answer directly with the binomial distribution, but it's way too much work. So the question is now, could we find a different distribution for x that would allow us to produce a much shorter solution? And the answer is yes, if we use the central limit theorem. Recall that the central limit theorem gives you a normal distribution approximately for a sum or an average of random variables. So our original random variable here was x. The question is, if we want to use the central limit theorem, we have to find a way to rewrite x as a sum or as an average of random variables. Well, think of how you would proceed in finding the value of x, the total number of people in your sample that do own a cell phone. So you would ask person 1 whether or not they own a cell phone, and you would get a yes or no answer. If the answer is yes, so if you have a success, you add 1. If the answer is no, you have a failure and you add 0. So each person is a Bernoulli experiment, a single trial that results in a success or in a failure, and we know the probability of success and failure for each trial. So think of it this way now. View each individual from your sample as a Bernoulli random variable. So say we have x1. This is the answer of person 1. Equals 1 if the answer is yes, equals 0 if the answer is no. Same for the second person up to the nth person, which is 120. And all of these are Bernoulli with the probability of success p of 0.7. And now, if you think of it, well, how would you get the total number of successes? Well, for every person, you add 1. So think of it. You ask person 1. If the answer is yes, you add 1. If the answer is no, you add 0. But that's what x1 is. x1 equals 1 if the person says yes, so the person does own a cell phone. x1 is 0 if the person doesn't. So x would be x1. Now we ask the second person whether or not they own a cell phone. If the answer is yes, we have a success, we add 1. If the answer is no, we have a failure and we add 0. Hence we add x2. And we keep asking each person up to the nth person. And now what we have done is we have decomposed our binomial random variable as a sum of n Bernoulli random variables. Now the central limit theorem says that a sum of random variables will be approximately a normal random variable as long as n is at least 30. Well, in our case, n is 120, which is well above 30. So here we can use the central limit theorem, which says the sum of the random variables is approximately normal. And now we need, if you remember, to find the mean of each random variable and the standard deviation. Well, x1 through xn are Bernoulli random variables, and if you remember, a Bernoulli random variable has a mean of p, and in our case p is 0.7, so the mean is 0.7, and has a variance of pq. Well, p is 0.7, q is 0.3, so we do 0.7 times 0.3, and we get 0.21. We need, of course, the standard deviation. Well, the standard deviation is the root of the variance. So sigma will be exactly the root of 0.21. And leave the exact answer as it is. So now we know the mean of each random variable, x1 through xn. The mean is 0.7. And the deviation is the root of 0.21. That's all we need, right? And because n is above 30, we can use the central limit theorem, which says that the sum will be approximately following a normal distribution. And we need to figure out the average, the mean, and the deviation. Well, the mean, if you remember, is going to be n times mu. And the deviation, be careful, will be root of n times sigma. But now we know n is 120, we know mu is 0.7, we know sigma is root of 0.21, and now we can plug it in. This will be normal. And mu, 120, times 0.7. This is 84. And the deviation, well, root of n 120 times the root of 0.21. And here we have an approximate answer. If you compute this here, you'll find that the root of 120 times the root of 0.21 is approximately 5.02. Now what we can do if we want to keep the exact answer is combine the square roots as a single square root. If you remember, because we only want to round up at the very end of our calculation, but the root of something times the root of something is the product, or I should say the root of the product. So it's the root of 120 times 0.21. And if you compute 120 times 0.21, you will get 25.2. So leave the exact answer for your deviation. Root of n, root of 120 times sigma, which is root of 0.21, is the root of 120 times 0.21, and that's the root of 25.2. And now we're good to go. The idea is now, before, we thought of x being exactly a binomial distribution, so we found the probability using the binomial distribution. Well, we could have, but we said too much work. Let's find a different distribution. And now with the help, and here, we could write comma CLT2, mention that we are obtaining this result with the use of the central limit theorem. And now you see what we have is a new distribution for x. We used to think of x being binomial, and now we forget this and we think of x being normal. So now this is our conclusion. X is, by the central limit theorem, approximately a normal random variable with a mean of 84 and a deviation of root of 25.2. And now we can find the probability of x being above 90 with our normal distribution, as we have done in the previous videos. So let's move on to a different page and just rewrite our distribution for x now, which is approximately normal. But because n is well above 30, we'll have a really good approximation. And recall that what we wanted to find was the probability that x was at least 90. So we wanted, first let's rewrite x, which was approximately normal, from the central limit theorem, with a mean of 84 people owning a cell phone and a deviation of the root of 25.2 people owning a cell phone. And we wanted the probability that at least 90 people from our sample owned a cell phone. And now if you remember, if you have now a normal random variable and you want the probability of that variable, you have to standardize because we only have one table, and that table is for the standard normal distribution. So we have to standardize, and if you recall, that implies subtracting the mean from everything. The mean is 84, so we subtract 84 from both quantities. So we subtract the mean, and then we divide by the standard deviation, which is the root of 25.2. Since we only subtracted and divided by a positive number, the inequality is preserved. I should have used slightly bigger brackets here. Now we have standardized. So what do we have here? Well, if you take a normal random variable, you subtract its mean, divide by its deviation, this is now the standard normal random variable, which we always denote by uppercase Z. And now we can finally compute this value and round off to the second decimal place, because as you remember, our table is only accurate to the second decimal place. So we do 90 minus 84, which gives us 6, and we divide 6 by the square root of 25.2. And we get approximately 1.195. So we'll round this off to 1. And here you have two options really. It's 1.195. So you could round up to 1.19 or 1.2, and that would really not be a big deal. Here, let's say we round off to approximately 1.2. So 1.20. Now we're good to go. This is now the probability that Z, the standard normal random variable, is at least 1.2. Well, there's only one little pickle here, and that is, if you remember, the table only gives us the area to the left of a given z-score, and now we want the area bigger than 120. So if you draw your distribution, and that's something you should always do. If you're ever unsure of what to do next, after you standardize, draw your distribution. So we have the standard normal distribution. The mean is 0. And we want the area, so the probability of z being bigger than 1.2. So we want the area of the right tail starting at 1.2. And again, the table gives you the area to the left. So here we have two options. We can use the fact that the distribution is symmetric, about 0, and look at the area to the right of 1.2 being the same as the area to the left of negative 1.2. And you could have also used, if you wanted, the complement rule. You could have said, I'll take 1, I'll add everything, and then I will subtract the area to the left of 1.2, and that would give you the area to the right of 1.2. Either method is fine. Here, let's just use the symmetry. So the area to the right of 1.2 is the same as the area to the left of negative 1.20. And now we can read this off directly from the table. We have a negative z-score, so we use the first side of our table. Let me just move this for a second. The z-score was negative 1.2, so we go down, negative 1.2, and you see it was negative 1.20, so we use this column. And with a z-score of negative 1.2, the probability is 0.1151. So we have our answer. It's approximately 0.1151. So if you sample 120 people from a population where 70% of people do own a cell phone, the probability that out of your 120 people that at least 90 own a cell phone, the probability will be approximately 11.5%. Let's see if we had used the complement rule just for a check that we would have obtained the same answer. So, or, as we said before, we could have done add the area of the entire distribution curve. So this would be 1. And now subtract, because we wanted the area to the right. So subtract the area to the left of 1.2. We can now read this from the table. Of course, we have a positive z-score, so we have to use the other side of our distribution for non-negative z-scores. And this is 1.2, so 1.2 is right here. 1.20, the probability, so the area to the left of 1.2 is 0.8849. And if you subtract from this, subtract from 1 this number, you get, as before, 0.1151. So you can always use whichever method you want. You can use the symmetry or the complement rule, and both are very natural if you look at the picture of the normal distribution. So this is our first application of the central limit theorem. We find the probability, and that's not exactly 11.5%, but it would be very close to, because we had way more than 30 people. We had 120 people. So you could try now, if you wanted to, brute force, add all these probabilities, do all of this work, either by hand or with Excel, and you would find the exact value. And if you do, you'll find it will be really, really close to 11.5%. So that's a really neat application of the central limit theorem. Every time you have a binomial random variable that for which you want a probability that involves a lot of work, if you have more than 30 trials, you can always fall back on the central limit theorem, which will give you, instead of a binomial distribution, it will give you a normal distribution. And then you can simply find the probability in 2 steps, which is the first step, standardizing, subtract the mean, divide by the deviation, and then tweak a little bit the answer to use the probabilities coming from the table for the normal distribution. And that is how you use the central limit theorem.